This video is with regards to the multiplication of matrices. So it says to determine if two matrices can multiply, you can do one of two things. Okay, so multiplication of matrices is slightly more, has a little bit more thought to it compared to addition and subtraction. So what you do, you count the elements of the rows and the columns. Okay, so you must have two matrices to multiply. So reading from left to right, because normally in the English language, we start from the left, reading towards the right. So reading from left to right, the matrix on the left, we can call it the first, and the matrix on the right, we can call it the second. So the row of the first matrix, that's the one on the left. The row of the first, the row of the left one. Okay, that have to be registered, row of the first matrix. You count the number of elements in the row of the first matrix. Then the column of the second matrix, the matrix on the right now, because you're moving from left to right. So the column of the second matrix. What you do, you count the number of elements in the column of the second matrix. Now, if those two counts are equal, then multiplication is possible. Okay. That has to be registered. The number of elements, not the number of rows, the number of elements in the row of the first must be equal to the number of elements in the column of the second. Now, it says that you can also compare the columns and the rows. Okay, so if you're looking at the columns now, okay, the first method is looking at the elements in them, but now we're looking at the columns and the rows themselves. So you count the number of columns in the first matrix. You count the number of rows in the second matrix. So if the two counts are equal, then multiplication is possible. So for the second method, you count the columns and the rows. Okay. But the columns of the first matrix must be equal to the columns of the second matrix. Okay, so either you count the elements or you count the columns. If you're talking about the elements, then you have to talk about the elements in the row, elements in the row of the first, and then elements in the columns of the second. I prefer the first approach, and you're going to see why. But if you want to analyze it using the columns and the rows, forget about the elements, but you want about the columns, then the columns of the first must be equal to the rows of the second. Now let's move on to the multiplication process now. The multiplication process, you have to identify the elements in the rows of the first. That's why I prefer the first method. Now for the multiplication, you must go inside the row of the first. Okay. And you have to go inside the columns of the second. And then you map the elements correspondingly. And you multiply the corresponding elements. And then you have to add the products. And you repeat that until all the pairs of rows and columns have been dealt with. Okay, so the multiplication of matrices involves addition. Okay, so you have to multiply and you still have to add just to get one element in your product. Okay, so we'll be doing that with examples, but we'll be referring back to the steps, if you want to put it that way. Now, scalar multiplication. Scalar multiplication is basically when you multiply a matrix by a number. So simply multiply each element of the matrix by that number. So if there's a number outside of a matrix, each element must be multiplied by that number. Okay, like you distribute that number to all the elements inside of the matrix. Okay, and here you have examples, and here it is done. Scalar multiplication. So 2 by 8, you have to multiply 2 by 7, by -1, by 3, by 0. Here it is. And you have 14, 6, -2, and 0. Scalar multiplication. Scalar multiplication is different from matrix multiplication. Okay. And here you have an example of multiplying A by B. So A by B is A by B possible? So if you want to take the first approach, we have to look at the elements in the row of the first. So you have 1, 2. The elements in the column of the second, 1, 2. So multiplication is possible. Now if you want to take the column row method, you have to count the columns in the first matrix. 1, 2 columns. How many rows? 1, 2 rows in the second, so multiplication is possible. Okay. Is AC possible? Just before we move on, let us see if AC possible. Let's take the elements approach. So A has 1, 2 elements in its column, and C has 2 elements in its row. A has 2 elements in its row, sorry. You have to try to be very careful not to confuse. Okay, so 1, 2 in the row of A, 1, 2 in the column of A. So a multiplication is possible. So although addition A plus C is not possible, but multiplication is possible because you've got 2 elements in the row of A and 2 elements in the column of A. Now, if you have to take the column row method, let's count the columns of A. 1, 2 columns. Now let's count the row of C. 1, 2. So again, that proves that multiplication is possible. Okay. And here it says, back to A times B. A has 2 elements in its row, 7 and -1. B has 2 elements in its column, -4 and 2. So multiplication is possible. And here it repeats, multiplication is possible. Multiply the elements of the rows of A to the corresponding elements of the columns of B, then add the products. So if you have to multiply A by B, that's 7 have to map to -4, and the -1 have to map to 2, row by column. So 7 times -4 plus -1 times 2. 7 times 5 plus -1 times 1. As I say, you have to do that for all the pairs of rows and columns. So in the first row, first column, first row, second column, that will give us the first row in the product. And the second row now, 3 and 0, we have to repeat that with 3 and 0 to -1, 2, 3 and 0 to 5 and 1. Okay, so 3 times -4 plus 0 times 2. 3 times 5 plus 0 times 1. And here we have the final product of A by C. One, just to put an afterthought, the product, the answer, you can predict the answer, the size of the answer, by looking at the elements that are the matrices that are multiplying. The rows of the first matrix will control the rows of the product. So because A has 2 rows, the final answer will have 2 rows. So the columns of the second matrix will control the columns of the product. So because the second matrix has 2 columns, the product will have 2 columns. So it's a 2 by 2. We can apply that now to A times C. A has 2 rows. Remember, we said A times C is possible because you have 1, 2, 1, 2. So because A has 2 rows, the final answer will have 2 rows. And because C has 1 column, the final answer will have 1 column. And just for proof of answer, let's look at a website, that an online calculator that can be very helpful, Symbolab. So here we have typed in the A times C in Symbolab, and let's see what we get. Remember, we said we're going to predict our answer is going to be a 2 by 1, 2 rows and 1 column. For a column matrix, it will look like C. And yeah, 7 times 6 plus 5 plus -1 times -2, and 3 times 6 plus 0 times -2. So let's see what the answer is. And here Symbolab has given us our answer. We'll click our button, 44, 80, 18. Okay, 7, 6 is a 46. Okay. And no, 76 is not 46. What am I talking about? 76 is 42. All right. And negative 1 times negative 2 is 2. 42 and 42 is 44, as you can see. And 3 times 6 is 18. 0 times negative 2 is 0. 3 is 18. 14, 18. And it shows you some steps. Here it is. Okay, well, a little bit of explanation. So you can use Symbol Lab to cross-check your answer, and it gives you some example also. This video presentation is with regards to the properties of 2x2 matrices. First, we're going to talk about the determinant. So the determinant now is calculated by finding the difference, meaning the subtraction between the product of the leading and the non-leading diagonal. So the leading diagonal now will start with the first element and diagonally go down to the last element. That is the one in the second row and third column, second row, second column. And that will form the leading diagonal. And a non-leading diagonal will start from down, go up diagonally. And as you can see, is from the element in the second row, first column, go up to the first row, second column. So you multiply those two elements. As you can see, they are color coded. A11 times A22 minus A21 times A12, because that's what difference means, the difference of the products. And that is called a determinant. So the notation for the word determinant is two vertical lines. So if you see a matrix with two vertical lines instead of a curved brackets, you've got to say determinant. So in words now, the determinant of matrix, of this matrix, or you can say the determinant of matrix A, and symbolically, that's how it is written. So when you see this, you must not see the matrix. This is not the matrix. This is the determinant of that matrix. So the word for those two vertical lines here is a determinant. Two vertical lines in another word, in algebra is absolute value or modulus. But in matrix language, two vertical lines, the word for two vertical lines is determinant. So if you see two vertical lines and there's a letter in between two vertical lines for matrices, you've got to say determinant, the determinant of E. That's how you read that notation. So the determinant of this matrix is A11 times A22 minus, always minus, that's the leading diagonal product thereof, minus the product of the non-leading A21 times A12. So for example, if you want to find the determinant of this matrix, so you've got to multiply negative 2 by negative 4 minus negative 1 by 3, or you can say 3 by negative 1. So you can go down, go up, or up, go down. Okay. And here it is 8 minus 3 is 11. The determinant of a singular matrix is 0. So singular matrices, their determinant is 0. So here's an example. The determinant of this matrix, A11, A22, minus 3 times minus 4 is 12. 2, 6 is a 12. 12 minus 12 is 0. So this matrix, minus 3, 6, 2, minus 4, is a singular matrix because its determinant is 0. So that's how you find the determinant of a 2 by 2, and that is the notation for determinant, words and symbols.